This video is about the quadratic basics. We're going to be talking about three different forms throughout quadratics. You're going to deal with factored intercept form, standard form, and vertex form. Factored intercept form is written as f of x, or a y, equals a parentheses x minus m parentheses x minus n. Factored intercept form actually, it's in factored form, so if you know how to factor, you can get it into this form, and it will give you your intercepts. It will give you your x-intercepts. So factored intercept form gives your x-intercepts. You'll end up being able to figure out what your x-intercepts are from your m value and your n value. Standard form is if you just a normal quadratic trinomial, so it would look like f of x equals ax squared plus bx plus c. This is just a normal quadratic, one that you've seen before with factoring. Now standard form, you can factor it to get into this form so you can get your x-intercepts, but standard form will actually automatically give you your y-intercept. So it gives us our y-intercept. And that'll actually be the c value. It'll be 0, c. Just like in a linear, it's your mx plus b. That constant term in most functions will be the constant term will be the y-intercept. And the last form that you're going to look at is called vertex form. It's f of x equals a parentheses x minus h parentheses squared plus k. Now this is also comes from function notation. It's very similar to function notation because of that vertex. So vertex form will, as the name says, it'll give you your vertex. So we'll automatically be able to find our vertex. So we have x-intercepts, and generally we'll have we should have two x-intercepts. Sometimes it'll be two distinct x-intercepts. Sometimes it'll be one x-intercept, but it technically happens there twice. And then sometimes we'll have two solutions. They're called solutions. Another word for intercepts is solutions or roots or zeros. So I'm going to write that up here. Another word for this, x-intercepts, are solutions, roots, and zeros. Those are three other words for x-intercepts. So when we get into solving quadratics, you could have two solutions that aren't actually crossing the x-axis. They would be called imaginary. So the quadratic would actually be above the x-axis, but still technically has two solutions. Okay. Every quadratic has to have a y-intercept because your graph will continue going left and right forever, so it will end up crossing that y-axis somewhere. It has to. It doesn't always have to have x-intercepts, like actually crossing the x-axis, because the graph could just be above it, because it could just keep opening up but never actually come down far enough. And all quadratics have to have a vertex because it has to have that point where it changes direction again. So that vertex is where it changes direction. So on our graph, we have multiple points. Obviously we have x-intercepts. We're going to have two x-intercepts. So these will be our two x-intercepts. So x-intercepts, which again can be called solutions. I'm going to write that again, solutions, roots, and zeros all mean the same thing. This is also an x-intercept. We will have a y-intercept, which is where it's crossing the y-axis, so at this location. This is our y-intercept, which you actually have, because it's a parabola, and these, do you notice that these are on the same, the y value of it? If I can draw a line through it, I can also do the same thing on any point on the graph. It'll be at the same location, y location, just on different x locations. So I can actually find the mirror of this y-intercept by just going over to the other side of the parabola. So this would be the mirror of the y-intercept. You don't always have to graph this, but it's always good to have 5 points. And you have 2 x-intercepts, a y-intercept, and a vertex. That will give you only 4. So if you have the mirror of a y-intercept, that gives you 5. But you can find the mirror of any coordinate. I can find any value and find a coordinate on it, and then mirror it to the other side. You will also have your vertex. Your vertex is at the either top or bottom of your graph. It's because it's where it's turning. That's your minimum or maximum value. This is your vertex. Now there is something else that you have to know. The reason why we're able to mirror these is because these are symmetrical, and there is called a line of symmetry. It's where you can fold the graph to make the mirror images touch each other. And the vertex, since that doesn't have a mirror part, that's where the line of symmetry would go through. Now that line of symmetry, if I were to fold this, I would fold it this way. So that's going to be a vertical line, and it's going to go through the vertex. So this vertical line that goes through the vertex is called our axis of symmetry. Or for short, it's our AOS. Now our axis of symmetry is an equation, and since it's a vertical line, it has the equation x equals a number. Now it's actually, the x value is actually going to be the x value of that vertex. So if you have your vertex, you just say x equals that x value, and you have your axis of symmetry. So x equals the x of the vertex, so the x value of the vertex. And it will be a number. So we know that that's going to be an equation. Your vertex is going to be a coordinate. It's going to be an x comma y. So you know x is going to be equal to that x, so the axis of symmetry. For your y-intercept, the y-intercept is also a coordinate. It's 0 comma a number. The mirror of your y-intercept will be the it'll be an x value, but it'll be the same y value of your y-intercept, but it'll just be a different x value. Your x-intercepts will be a number, comma 0. Both of them will be. Now, obviously, they will be different x values, but the y value will always be 0 for your x-intercepts. Because it's the intercepts, it's crossing the axes, part of it's going to be 0. So on the x-intercept, you have an x value, so the y is 0. The y-intercept, you have a y value, so your x is 0. So it's important that you get 5 points. You do want to have 5 points so you can make a graph accurate. So I'm going to put a note down here. You want 5 points to make your graph accurate. 5 points to make your graph accurate. That's the 2 x-intercepts, the y-intercept, the mirror of the y-intercept, and the vertex. And again, if you find another coordinate and you can do the mirror of that, that works as well. Now, if we look back at the equations, all of the equations have an f of x, which stands for y. They all have x's in it. They all have a's in it, but then all the rest of the letters change. That's because the other letters are what give you your x-intercepts. Your m and n are your x-intercepts. Your c value is what gives you your y-intercept. And the h and k are what give you your vertex. So f of x stands for y. X stands for x. So what does the a stand for? So that's what we're going to talk about. It's all about the a. The a tells us so many different things. So if the a is positive, if the a value is positive, and the a value for all of these, if I'm dealing with one graph, the a value for this is the same a value as that and the same as that. So all a values will actually be the same. So when we convert them, all of the beginning terms should always be the same number right here. So if the A value is positive, your graph will actually open up. That means that the arrows are pointing up, and that means that it's called a minimum. You have a minimum value or a minimum vertex. So this one is where our A would be positive because it's opening up. This one would have an A value of positive. Now if it's negative, that means that the graph will go towards the negatives. That means it's opening down. So if it's opening down, the graph would go like this, and you'd have a point up here. Your vertex would be up the top. That would be a maximum value. It will also, because we're going to be talking about transformations and function notation, just like up here, this function notation. If the A value is negative, you would actually say, because it opens down, that it reflects over the x-axis. It is a reflect over the x-axis. So if A is greater than 1, so if it's bigger, if you think about slope, if your slope is a larger number, it's more steep. So A is bigger than 1 is where it's going to actually stretch the graph. It's going to make it go faster. So instead of going at a nice slow pace, it'll go really quick. It'll get to the next coordinate much quicker. So this is going to be called a vertical because it's stretching up. It's a vertical stretch. If A is bigger than 1. Now, if A is smaller than 1, but it's still bigger than 0, so the whole thing negative, I only want the actual value of A, the number itself, because the negative tells me something completely different. Okay, so if A is bigger than 1, it's going to be the vertical stretch of A. Whatever that A value is, the absolute value, the positive of it. But if A is between 0 and 1, so that means like a fraction, a proper fraction, that means that it's going slower. So it's not going as fast, so it's not going to go up as quickly. So it's going to be kind of pushed down more, it's going to be fatter. This is called a vertical compress. Because if you think about a soda compressor, the can, it squishes it. So a can would normally look like this, but when it squishes it, it flattens out and it goes fatter. So a vertical compress of whatever that A value is, again, it's the positive value. That's why it's between 0 and 1, because the negative tells you something completely different. So this is all about the A, and it tells you information about the graph itself. And this part, specifically this blue right here, tells you about the transformations when we talk about function notation. Now, let's talk about the domain and range of a graph. Domain is the x values. Domain is the x values, and you actually read left to right. Because when we graph something, and when we read from left to right. If I was reading this, I would read it vertical compress of A because I'm going from left to right. So a graph is also going from left to right. So as I go from here, as I go to the right-hand side, I have to follow the graph. So I go down, and then I start going back up. So I'm going from left to right. The domain is, we're going to be writing an interval notation. Interval notation, because domain and range both have a start and stopping point. So I want to know where the start and stopping point is, and then what it is. You have the start point and then the stop point and then everything in between it, but you don't have to write out everything in between it because that will take forever. So for domain, it's the x values. If you're reading it left and right, your graph is going left and right. So the question is asking, does this graph, okay, if we're talking about from the axis, from 0, if I'm talking about 0 here, does this graph go to the left forever? This graph, because of the arrows, it will keep going left. It's going up and left because that's diagonal. So it's important that that keyword left is said. It is going left forever. The right-hand side, this graph will also keep going right forever. It'll never stop. So there technically is no start or stopping point. So in order to write that for domain, our domain for quadratics, because it's going left and right forever, is going left forever, so it'll hit negative infinity. Negative infinity, because it's going to the negatives forever. It is going to the negative x values forever. But comma, I'm going to put a comma because this says everything in between it. So all the way from the beginning of the left-hand side, and it's going to go all the way to the end of the right-hand side, but we technically don't know where that ends, so it's going to go to the positive infinity. Now, I have to actually use the notation for this, for intervals. I'm going to use an open bracket for both of these. Now, again, these are called open brackets. Open bracket. And the reason why it's called an open bracket and why I didn't close it is because infinity actually never gets hit, because you don't know what the actual value of infinity is, so it doesn't actually stop at a number. It doesn't stop at a actual number, because infinity keeps going on forever. It would literally take you forever to figure out where it stops, because you couldn't. The way we pronounce this, I'm going to say this again. This is pronounced negative infinity to positive infinity. Because this is saying negative infinity and it goes to, so that's what the comma is for, to positive infinity. And it'll include everything in between there. So the domain, again, are your x values, so left and right. So if we're talking about the range will be our y values. Y values. Where range will be, since it's the y values, if we went from left to right, so we basically went from the negatives to the positives, we're going to do the same thing for the range. We're going to go from the negatives to the positives. So we're going to read from the bottom to the top. So read bottom to top. We're also going to use interval notation for this as well. But the difference is on quadratics. Quadratics don't have to go up and down forever. They can go up forever, but do you notice on this one, it doesn't, the arrows aren't pointing down, it's not going down forever. It actually stops and then comes back up. So this one would have a specific type of infinity to use. It doesn't have both. Domain had both because it's going left and right forever, but ranges won't have both, because it's going to have to either go up forever and be a minimum value, or it's going to have to go down forever and have a maximum value. So it will stop. It'll curve somewhere and then go back in the direction it came from. So for a range, we actually have to write out what the two possibilities are. Because we can have a minimum value and we can also have a maximum value, we have two possibilities for our range. So if the graph opens up, so if our A value is positive, so opens up, that means that it's going to keep going up forever. We will have a positive infinity. Now, following this part, the positive infinity, and just focusing on the infinities only, the positive infinity is on the right-hand side of the comma, because that would be the stopping point. So our positive infinity would actually go on the right-hand side of the comma. So what goes on the left-hand side? That's our starting point. The starting point of the y of the graph. So where does the graph actually start? Which coordinate does it start at? It starts at the vertex, because that's going to be the actual minimum. So we want the y's, because this is range, so do we want the x or the y? And we want the y of it for the range. So this part of our range is the y of the vertex. Y of vertex. So let's talk about the opened and closed part. Infinities never actually get hit. So on my positive infinity, I need to make sure I have an open bracket because I know it's not going to stop there. But on the y of the vertex, it actually does stop there, and then it goes back up. So it hits that point. So I'm not going to have an open bracket. I'll actually use a closed bracket for that because it actually hits there. And I'll write out to the outside what that means again. But we can also look at if it opens down. If it opens down. So if our a value is negative. So if it's going to open down, the arrows will point to the negatives forever. So does it have a starting or a stopping point? So again, we're reading it from the bottom up to the top. So it stops up at the top. It stops second. So our stopping point is going to be at the end. Our stopping point is going to be at the end. That means that our infinities it goes down forever, so our negative infinity is always written in the first spot. So we put negative infinity, and because it doesn't actually hit it, we know that's going to be an open bracket. But it will stop somewhere. And again, it stops at that vertex because that's the highest or the lowest point. And it's range, so we want that y value of the vertex. And since it stops there, we can use a closed bracket. So again, I'm going to write out what that means again. The closed bracket. So this thing too, closed bracket. I'm going to draw a little arrow over here. This is a closed bracket. And it's because it literally stops at a number. It'll stop at that y value of the vertex because that's as far as it can go. So this is just the basics of quadratics, understanding the domain, the range, the different coordinates, what the a value does, and just the equations that you're going to be looking at because we have 3 different equations because it gives you your different information.